Good afternoon. Thanks for coming. My name is Yang Ren. I'm from Physics Department. It's truly an honor for me to introduce the speaker of today's lecture, Professor Hezhen Chen. Professor Chen is a particle physicist and academician of Chinese academic science. He received his PhD from MIT in physics, and he's currently the head of a command and engineering manager of China spallation neutron source. This is one of the 4 in the whole world. So it's in terms of the spallation neutron source. Professor Chen used to be a director of Institute of High Energy Physics and the president of the High Energy Physics Society of China and vice president of Chinese Physical Society. Professor Chen is the co-director of the joint laboratory and of our center of for neutron scattering here in our university, and so only one, I think, in Hong Kong in this field. And Professor Chen has many major contributions, especially in the high energy physics, like discovery of the gluon jet and symmetry study of gluon physics in Mark J experiment in DAISY, and also a lot of contributions to the precision measurement of electron weak parameters and demonstrating the validation of the standard model. China contributes a lot in the high energy physics, especially in developing the large area detectors. One of them is called the LC detect system. I think it's one of the 4 large ones in CERN. And so you can see this is not like your lab experiment, more or less the huge facility. So I think today Professor Chen will talk about the South Advanced Photon source. Good to see all of you here. And it's not about science. We're talking about the future workforce, workplace. And I think you used to study or learning or working in this confined lab in CTU in Hong Kong. If you have a chance to visit a so-called large facility, you can drive a car inside of the facility even. So normally, what you feel is totally different. And we have one in Beijing. Now we want to build another one next to Hong Kong. So there's a lot of job opportunity, I think. And so let's welcome Professor Chen to give our perspective and the future plan for South Advanced Photon source.
Thank you very much for the invitation. So the single-strand radiation was a bottleneck for the particle physics accelerator because the energy consumed in the single-strand radiation is e to 3 or 5, means increasing very fast when the beam energy increasing. So it's the bottleneck for us to build the large high energy accelerator. You heard about there is a proposal to build a CEPC, which is 100 kilometer circumference. Why is so large? Because smaller circumference, they were much stronger single-strand radiation. But in another hand, we found the single-strand radiation was very useful for the many studies in the material science and life science. So in the 1974, a dedicated single-strand radiation facility was built. So the advantage is the single-strand radiation source is extremely bright with the energy concentrated over several narrow angles in the order of arc seconds, about 10 microradius. And compared with the conventional light source, the single-strand radiation could offer many advantages, including the broad spectrum, high brightness, excellent collimation, and adjustable wavelengths. So synchron radiation became a critical platform supporting the cutting-edge research and the development of high technology applications for the many display lines. So when the single-strand radiation go into a sample, you can see the many ways to study photon electron, reflection, deflection, fluorescence, and the inelastic scattering. So we have many ways to study it. This is a sketch of the single-strand radiation source. So it consists of 4 parts. First is the injector. Normally is a Dirac electron. Then is the storage ring, is a circular path where the electrons accelerate and maintain at a high speed. Then is the beam lines, directed emitted radiation from the storage ring to experimental area. You see, this everyone is will produce very strong light. So at the very beginning is the bending magnet produce a single-strand radiation net. And afterwards, we use the Wegener. It's a special magnet to make the electron beam up down and produce strong light. And now we use the modulator, Schoenberg conducting modulator, which is much stronger to produce more strong light and more coherent. Then we have an experimental station, conduct experiments use the single-strand radiation. So around the storage ring. The major features of the single-strand radiation is their high brightness and high flux, continuously, tunable spectrum, high stability, excellent collimation, precise time structure, and adjustable polarization, and partially coherent. So that make many applications, imaging, scattering, spectroscopy, and Now it became a major scientific facility over the world. I just give some typical applications. First is there could be a super microscope, unable to exposure the microscope structure, compensation, and the dynamic process at the molecular and the atomic level, depending on the experimental method. So you can see they have many different reactions could be studied, including X-ray imaging, X-ray deflection, and fluorescence spectroscopy. All of these methods are very useful method to study the sample structure. Now there are already more than 60 single-round radiation light sources worldwide. And in China, there is in the 1990, there is Beijing single-round radiation facility use the Beijing electron pulsar collider is the first generation light source. The second generation light source is in the Hefei, that's in the single-round radiation lab. The third generation is Shanghai single-round radiation light source. Recently, the fourth generation single-round radiation source is called higher energy photon source built in Beijing. So you can see the time evolution versus the flux of the single-round radiation net. So it's increased from first generation, second, third. Now we go to the deflection limiter single-round radiation source is a fourth generation. If we want to go to further higher, then we have to go to free electron lasers, which is complicated and very expensive. So Shanghai is building hard X-ray free electron lasers. The fourth generation light source, the machine structure uses the MBA focusing structure. That could reduce the beam size and make the light more strong. And the radiation intensity will have about a factor 2 more than third generation. And they have significantly improved for the coherence. So I would like to explain you the major experimental technology and applications of the single-round radiation. So this is a long list for the single-round experimental techniques. So like the most popular is X-ray deflection. They study the crystal structure, phase compensation, and stress. X-ray absorption spectrum, they for the element valence status and the local structure. The photoelectron spectroscopy, they use the photoelectron to study the many interesting problems. Small angle X-ray scattering, they see the nano scatter structure in the polymer, colloid, and many biomolecular. Resonance inelastic X-ray scattering, investigating the electronic excitation and the bond structure used for the strongly correlated electron systems. X-ray microscopy provided the nanometer resolution imaging and the time resolved X-ray scattering. They could examine the dynamic process and the chemical reactions with the femtosecond to picosecond resolution. X-ray magnetic circular decoloration study the magnetic properties, especially the thin film and the nanostructure. Soft X-ray spectroscopy, they investigate chemical environment and the electronic structure of the low Z element. I give some examples. For the nano resolution X-ray fluorescence ghost imaging. So we use this method, we could get an imaging principle for TXM single pixel fluorescence detector and ghost imaging. This method achieves the nanoscale space resolution, composite and chemical sensitivity imaging, and provide a powerful research tool for fields like biology, environmental science, material science and technology, especially for the radiation sensitive samples. X-ray nano focusing enable in situ study the subcellular serology, facilitates protein molecular transport analysis, investigated the local defects in the low-dimensional and polymer composite materials, and advanced next-generation chip fabrication process, and examine the intrinsic structure of atmosphere particles. This is just some examples for the applications. The is a wide range for application. Further example is our X-ray autosecond bump and autosecond probe. Our X-ray autosecond bump, autosecond probe, this experiment are considered a direct method for real-time observation of the electronic dynamics. So they can measure the information of autosecond timescale following the X-ray interaction and study the liquid water for many IB1 peak and from the many process. This just some experimental examples. Number 4 is grazing incident X-ray photon correlation spectroscopy. Both the Argonne lab synchrotron radiation source APS-U is upgraded. They became the 4th generation. And the Brookhaven NSLS2, they two light source are development the GIXPS method is a coherent X-ray scattering technique based on the grazing incident geometry. The typical application used to study the dynamics of the thin film surface and the time scale range from the sub-microsecond to several hundred second. So that's the new development and very useful. The synchrotron radiation application areas including the biological and life science, material science and technology, energy science, environmental science, physics, chemistry, chemical engineering, pharmacies, medicine, and archaeology and geology. So it's a very wide application. It's most powerful multiple discipline platform for different research field. I give some example of applications. First is about the electronics and the information technology. With this, the challenge in the modern chip design is the intrinsic structure of the modern chips makes non-destructive imaging for the entire device, and its interconnection essentially is very difficult. And we use the coherent X-ray imaging. We could make a three-dimensional imaging and provide a significant benefit for the chip inspection and the reverse engineering. So the third generation light source could reach the 10 nanometer resolution, could successfully test the chips for about 16 nanometer. And the fourth generation, they could reach the chip for 5 to 7 nanometers. So this is the typical method to use this to study the modern chip design. So that's very important for the chip industry. And for the material genome engineering, so we have so many components, and we actually 60 stable elements. They could form 34,000 different components, and 97 of them are unknown. And also they have 500,000 possibilities for the different diagram, and almost all of them are unknown. So lesson 7+1, material major project. The 1 means the material genome engineering research platform, support for the development of supporting the development of the 7 major strategic materials. So the light source, together with the spectral source, provide a high throughput the platform to study the material genome. Third example is the drug screen. So the single-run radiation make a very important role in the drug research. The most successful example is the Argonne Lab, APS. So more than 230 drug companies work in the APS. So the data from the leading international pharmacy company indicated more than 30% of proton-related drug development have benefited from the argon APS light source. The China drug screen study also developed quickly, mainly in the Shanghai synchrotron radiation source. So they provided the important structure of many drugs. And in the Greater Bay Area, we have a lot of drug companies, biotech companies. So, and there is also Canton lesson lab for the life science, and they indicated a bigger demand for the synchrotron radiation. And chemistry and chemical engineering. The Canton has a very strong, very big chemical engineering, but particularly for the oil industry, oil chemical industry. But they do need development, the high-end production, and to addressing the critical bottleneck. The most important is the tracing the chemical reactions, precise material structure analysis. So that's the key issue is use the synchrotron radiation. And I would like to give you some successful sample from the Hong Kong scientists, particularly for the alloy steel material. The Professor Huang from Hong Kong University, they use X-ray deflection, obtain the precise information on the structure and the defect of their impact on the function for the structure material of the car, also for the functional material. This is their results. And for the small angle X-ray scattering, they provide the particle size and the distribution information for the cars. So they are precise, as small as the COVID-19. And they use the 3D X-ray deflection. They construct the 3D distribution of internal stress and loading conditions. So they obtained the many important results. And they use hard X-ray nanobeam to scan the entire material for the thickness fluctuation in the 10 nanometer, and so on. Second example is biomedical applications. So they use the synchrotron radiation light source to decode the protein structure and their function. The Professor Hao Quan from Hong Kong University, they, in the light source of the cornea, they discovered the molecular in the protein structure, uncovered the new function of the some new protein. And Professor Zhu Guang in the Hong Kong University of Science and Technology, they measure the crystal structure of the new type of the protein, DNA, and get very important results. These results came from the Shanghai synchrotron radiation light source. And for the new energy, the structure, the function for the new energy structure, they stabilize the Holocaust structure of lithium and rich LMR layered oxide, and design the LMR inhibit negative voltage. So they are cycling 50 times, and the structure was stable, and they are very useful for the new energy. Now I would like to introduce the proposal of Southern Advanced Photon Source. So there is a strong demand in the Greater Bay Area for the Southern Advanced Light Source. So the Greater Bay Area, the GDP already more than 13 trillion yuan, and is the #1 regional innovation. And Shenzhen, Hong Kong, Guangzhou technology cluster ranked #2 in the worldwide. The strong research capability in the Great Bay Area. So this will just show the light in the evening. We can see this is the Beijing, Shanghai, Canton, Bay Area, and Taipei. So we can see there is large concentrated economic and scientific activity in this area. And advanced light source is the standard configuration of the world famous Bay Area. The New York Bay Area, there is the Brookhaven NSLS2. In the San Francisco Bay Area, there is the ALS light source in the Berkeley lab, and a synchrotron radiation light source in the SLAC. In the Tokyo Bay Area, there's a Photon factory at the KEK, Japanese High Energy Physics Institute. The Southern Advanced Photon Source will support the development of the comprehensive National Research Center and the International Innovation Center in the Great Bay Area. There is the most economic development and to meet the strong demand in the Bay Area, Great Bay Area. So I think that the one reason is the large amount of users. So every light source, their user range, more or less, always is localized. So for users to go to Beijing or Shanghai, it's not so convenient, particularly for the life science sample. You have to put in the liquid nitrogen, and that's not able to go with the high-speed train or airplane. So you should have a photon source in the Bay Area for this type of research. So as I mentioned, there were complementary where is existing light source in China in terms of the energy range and the geography. I will go to detail later. Another advantage is the complementary of the neutron source of the synchrotron radiation. So this just to show example for the synchrotron radiation facility and the spallation neutron source. The synchrotron radiation facility uses X-rays, and the spallation neutron facility uses the neutrons. They go into the sample. The X-ray interactive with the cloud, electron cloud around the nuclei, and the neutron interacted with the nuclei. And we measure the outcoming X-ray and neutron. We can get information about the samples. So the synchrotron radiation is high dynamic range, high resolution, and could measure smaller sample. Neutron scattering had a high penetration, and they could measure the magnetic structure and in situ. So the two methods are complementary. However, the synchrotron radiation is much more popular. Already have more than 60 in the world. But the spallation neutron source, so far, we only have 4. The Rutherford UK light source called ICES, US spallation neutron source SNS, and the Japanese spallation neutron source called JPAC. And the China spallation neutron source in the Dongguan is number 4 in the world, finished finished at 2018. And the fifth spallation neutron source, the European spallation neutron source, is under construction in the Lund of Sweden. So because of the synchrotron radiation, because the spallation neutron source is more expensive, and the experiment is more challenging, and the operation budget is very high. However, the synchrotron radiation and the neutron scattering are the two flawless combinations. So the many researches require the integration of the both X-ray and the neutron scattering. They provide a rich research platform where 1 + 1 is far greater than 2. We give some example. In the Rutherford lab, they have a light source called Diamond, and also they have UK spallation neutron source ICES. In the Swiss lesson lab called PSI, they have Swiss light source and Swiss spallation neutron source. It's not a pulsed spallation neutron source, it's a continuous beam. And in the Lund, Sweden, they already have a 4th generation light source Max 4 and European spallation neutron source under construction. In the Grenoble of France, there's a European synchrotron radiation facility and high flux nuclear reactors. So these 4 examples show they are, in Chinese saying is 珠联璧合, provided the best platform for the scientific research. And we just give some example for the researches required both facility. For instance, for the lithium batteries, X-ray has the fast time resolution, charge and discharge dynamic process, high performance, high penetration of the neutron, and they could do it in situ charge and discharge process. So we combine these 2 methods could give a very powerful platform for the lithium battery. For the quantum material research, the neutron, they could study the lattice and the spin measurement. X-ray study the charge and the optical measurement. So this 2 platforms will provide the quantum material study for the strong correlation for the 4 key aspects. For the advanced manufacturing and the new materials, I think we have a big challenge for the stress study for the key mechanical components. So like the railway wire and airplane engine and many other items. So X-ray, they could do it stress distribution in the surface and the near surface region. Neutron could do it non-destructive detection for the bulk stain and their distributions. For the material science, the neutron-sensitive light elements, and X-ray sensitive heavy elements. Comprehensive analysis of the microstructure of material in the biology, energy, environment, and more. They need both methods. So this picture just shows with the neutron scattering, we can get such kind of rich molecular structure. But if we use the synchronous radiation alone, we will only get the white part. And the red part came from the neutron scattering. Another important application area is dual carbon gold. So there's many studied the combination of the neutron scattering and the synchronous radiation technique that determine the fine structure of heteroatomic zeolites. This research is considered to be a significant breakthrough in the field of carbon neutrality, provide a way for the many new applications. What we suggest to build the single-zone radiation facility in the Dongguan, in the Songshanhu Lake scientific facility. So the Dongguan campus of the CTU also is in this area. So they already have the spatial neutron source, and with the Shenzhen is building the high energy X-ray free electron assay, and they have we are proposing the single-zone radiation light source, and there is auto-second laser facility already started constructed in the same area. So this facility will form a cluster of a large research scientific facility. So particularly is very useful for the CTU. The goal of the light source, Southern Advanced Light Source, it will be 3.5 GeV. Beam brightness will be 10 to 22 photons per second per millimeter square mini radius. Emittance is less than 60 picoradius. That's the world highest. And the beam current is 500 milliampere. So this is the current facility. This is the spatial neutron source. This is the test platform for the Southern Advanced Photon source, and we are proposed to build a light source nearby. So the spatial neutron source and the Southern Advanced Photon source will give strong support for industry demand in the Greater Bay Area, including the electronics, information, life science and health, green and low carbon, new materials and intelligence equipment. So it's a very useful platform for Bay Area. Finally, I would like to report to you progress of the prepared work for the Southern Advanced Light Source. The idea actually came from the Canton government. They introduced the idea to build an advanced light source near the SNS at August 2017. And in the November 2018, Chinese Academy of Sciences and the Canton province government signed a cooperation agreement to push the Hong Kong, Canton, Hong Kong, Macau, Greater Bay Area International Science and Technology Innovation Center. So particularly they emphasize the Southern Advanced Light Photon Source. And IHAB and the Dongguan city government signed the agreement for the Southern Advanced Photon Source. In the year 2020, the National Development and Reform Commission and the Ministry of Science and Technology approved the roadmap of the comprehensive national research center in the Caribbean area. This is supported by province government and the Chinese Academy of Science. So they made a clear roadmap to build a Southern Advanced Photon Source relying on the spectral neutron source. So the advantage to build the Southern Advanced Photon Source in the Dongguan is we already have a spectral neutron source team, about 400 young professional specialized in the construction, operation, and the management of the large-scale scientific research facility. So this is the team and 2018. In another hand, the Dongguan team, Dongguan branch is part of Institute of High Energy Physics. So the Institute of High Energy Physics just finished the higher energy photon source. Is the fourth generation 6 GeV photon source in Beijing, north of the Beijing, the Huairou. So they finished the construction, now is in the commissioning phase. So the construction team with the technical expertise, equivalent manufacturing experience could establish a strong foundation for design and construction of the Southern Advanced Photon Source. And the Dongguan city government has provided 690 million to build the research and testing platform near the spectral neutron source. This is the spectral neutron source. This is the test facility. They provide the key facility for the high precision measurement, superconducting, radio frequency, and X-ray optics and detector technologies. So they provide they already finished the construction and provide a good foundation for the new light source. And the key technology has the R&D of key technology for the new photon source was carried out since 4 years ago. In the tech accelerator, we have the full energy, linear energy accelerator. And we have the storage ring design and use some new technology to reach the high performance. And for the experimental beam lines, we could have 6 beams lines in total, and 10 will be in the phase 1. And we are still optimizing the beam line design. And we have the many works for the R&D. And the site we chosen near the spectral neutron source, because the 4th generation light source require very special, very strict requirement to vibration. So they require less than 25 nanometer minutes for the 100 hertz. So if you go to see the loaned light source, which is first, fourth generation light source, between the roadway and the light source, they have a very complicated shape, the small here. So have about 5 or 10 small hairs artificially to absorb the low frequency vibration. Because the fourth generation light source, the beam is very narrow, very small. If the vibration is too big, the beam will be lost. So, and we investigate the spatial-induced area has a very good geological condition for the fourth generation light source. And we had many workshops for the light source design from the 2017, 2018, and 2023. We organized the steering committee for the design. And the last year, we have 11 working groups established. And also many companies like the BRD and many companies joined the discussion. And we have more than 100 presentations in the 11 working group meeting. The members came from the 95 university, research institute, and enterprise. Is more than 400 people. And we discussed the design of the light source and the choose of the beamline and expander station. So the 400 of them, 40% of them came from the Bay Area, and also 13 of them from the Hong Kong and Macau. So this is the list of the institutions. So in the phase 1, we are going to build 10. We drive the demand is for this 10 field, and based on this demand, we choose the beam lines. So I just give some examples. For the bio and the life science, for proton study, we have the macromolecular crystallography beam line. For the biological materials, we have a hard X-ray microscopy beam line. This is the major parameters of the beam line. And for the material science, we have the coherent scattering beam lines for the dynamic research. For the structure material, we have high Breton power diffraction. So this uses the X-ray deflection and measure the PDF. For the electron structure, we have a coherent scattering beam line. And for the structure with hard X-ray beam line. So this is the major parameters for those beam lines. For the environment and the energy, we have the study soft mat with the small angle X-ray scattering and the wide angle X-ray scattering beam line. For the catalysis and the thin film, we have beam line 7 for those kind of study. So last month we have signed the agreement with 8 Hong Kong Manco University to build a Bay Area flagship facility, Southern Advanced Photon Ship. So we will promote the more cooperation with Hong Kong and Manco. Finally is the summary. The Canton, Hong Kong, Manco, Greater Bay Area with the strong economy and innovation capability urgently need advanced photon source to support industry upgrade and fundamental research. Neutron scattering and synchrotron radiation are the key tools for the study of matter's structure and dynamics. Build advanced light source in the Greater Bay Area alongside with the spallation neutron source will create the world-class, cutting-edge public platform for large-scale scientific facility. Southern advanced photon source should be part of the national large research infrastructure plan, hosted jointly by Canton, Shenzhen, Dongguan, Hong Kong, and Manco. It will be a flagship of the comprehensive national science center of the Greater Bay Area. I think the joint host is the money contribution from the Hong Kong and Manco is less important. The cost probably is between the 3 billion to 40 billion Chinese yuan. So such kind of scale, I think that's the typical scale for the large research infrastructure in China. We propose to join the host is because once the Hong Kong and the Manco contributed, joined the host to the facility, their money contribution basically will promote the research in the Hong Kong and the Manco to get the team formed and join the construction, operation, and research. The construction plan and the initial beamline selection has been determined. The construction of a research testing platform and pre-research on the key technology has been completed, provided the necessary condition for the construction to be started. And the team and the technical expertise from the IHAB has provided a solid foundation for the delicate development of the higher energy photon source. So that's all of I'm going to report to you today. Thank you.
Thank you very much for a very nice talk. And so we do have a time for questions.
I just mentioned the CTU Dongguan campus, just about 3 kilometers in the east of the spallation neutron source, just in the desert side, 3 kilometers away. So they already established and already has education, particularly for the engineering school.
Yeah, it's by chance or luck. It's good for the CTU in Dongguan, I think. A lot of opportunities. Any question from the audience? Maybe I can start first. So you mentioned for the neutron, you so far have 400 employees working that. What do you think for the APS? Probably 1,000, huh?
Means we have 400 position is a permanent position, so-called 事业编制. Now we have about 300 PhD students and postdoctors.
Oh, okay.
So those people work for the operation of the circulation neutron source existing and the phase 2 upgrade of the circulation neutron source. The phase 2 upgrade, they basically is in this campus. So they will increase the beam energy. They will increase the beam energy of the LINAC from 80 MeV to 300 MeV. Then the fast cyclotron synchrotron could produce factor 5 more beam power on the target. So then they can have factor 5 more neutron flux. So that's the phase 2. So started beginning of this year, finished by 2029. So we are proposing to build the new light source. So once they decided, we certainly will hire the capable teams for this project. So now we already have some photon source experimental physicists work on in our Dongguan branch to prepare the photon source. So I think it will be in the scale of hundreds.
Okay.
Thank you for your talk, and I'm very happy to hear the progress of the APS. And I find that in your plan, for the phase 1, there are some beam lamps that, such as powder diffraction and absorption spectrum. They are very useful for our research since I'm working in energy materials. And I wonder when we will be able to perform experiments at the South APS.
You mean when?
Well, yes, I want.
I think because you see that we are pushing this proposal. So I think we wish it could be started construction by end of next 5 years plan, which means before 2030, we could start the construction of a new light source. So and it will take about 5 years to be built. So that will be 2035 for open to users.
Okay, thanks.
Okay, any further questions? Okay.
Thank you, Professor Chen, for the comprehensive talk. Maybe a question related to the previous one is, so if this synchrotron, the construction started, can we start to build the beam lines at the same time, like similar to ESS?
Yes.
Okay.
Yes.
So this
that's the typical way.
Okay.
We do it. Means in the high energy photon source in the Beijing. So when they start in the storage ring commissioning, they already have the synchrotron radiation light come out, and the beam line already ready to test the beam line experimental station and start the day 1 experiment. So that's the synchronized. I see. Because we want to get good results at day 1.
I see. So another question is, so there are some reason to build such a beamline as mentioned in your talk, like it's a good combination with the spallation neutron source. But in terms of the synchrotron itself, is there any advantage compared to the existing synchrotrons? Like some
You mean compare with the existing facility?
Yeah, with the existing facilities.
So the Beijing high energy photon source is 6 GeV fourth generation. The Hefei, they are building lower energy fourth generation is 2 GeV. And for the 3.5 GeV is Shanghai synchronous radiation light source is third generation. As I mentioned in my PPT, so the fourth generation means the southern advanced photon source, the photon flux will increase 2 magnitude compared with the Shanghai third generation light source, and much more coherent, so it will be much more powerful. So as I mentioned, the European light source, argon light source, longer, they already upgraded to the fourth generation. So that's the international doing. So we have built a medium energy photon source at 3 GeV. That's the southern advanced photon source. It will have factor 2 magnitude higher flux and much more coherent.
Thank you. Do you have a further question? Anyway, I want to remind you, and also to assure you, working in that terrain is very enjoyable, and also the neutron. It's really most important thing. You want to make something work, really, real work, rather than you just focus writing papers, something like that. And every day you're busy with something, you feel, very, very fulfilled with some sort of instrument development, science results, and this is a good opportunity. Anyway, if there's no further question, because we have to catch up another event, so let's thank Professor again. Thank you.
We have a long history collaborating with CTU, and now the Dongguan campus CTU very close. So I wish we could have more collaboration with spallation neutron source and for the future light source. Thank you.
Thank you.